This is a quick sketch, a pressure vessel, where we have in fact just drawn 1/2 of the pressure vessel. It would be symmetric about the plane on the bottom here. It is 50 centimeter outer diameter and 48 centimeter inner diameter. And it was then pressurized. That's what these green arrows are showing. It was pressurized to 40 MPa so we could see the stress state inside this pressure vessel with a hemispherical end cap on top of it. Now, the interesting thing about the hemispherical end cap is that the stresses in the hoop and radial directions in the hemispherical end cap are always on the order of PR over 2T. They match the longitudinal stress along the long axis of this pressure vessel, but they do not match the PR over T hoop stresses in the cylindrical part of the pressure vessel. And so because of that, we end up with a change in the stress state as we move from the cylindrical to the hemispherical end cap. So we can take a look at this and we could compare the numerical values of the stresses to the hand calculated values, which I will do in a bit. But the first thing that we want to do whenever we look at these is we want to make sense of the stresses that we are seeing. And so I have said that the hoop stress that would be sticking out of this wall thickness right here is going to be twice the value up here in the hemispherical part of the end cap. So the hoop stress in the cylindrical is going to be twice as big as the hoop stress out in the hemispherical part. And though this is a pretty coarse mesh, we can go ahead and create a point probe and take a look at this. And if we do that, we will find the hoop stress in the cylindrical portion is on the order of 463 MPa. And when we go up here, the hoop stress is on the order of 214, roughly half of what we get down in here. I show here an example of an Excel spreadsheet that I use to calculate the tangential, the radial, and the longitudinal stresses in a cylindrical pressure vessel. And these are only in the wall of the cylindrical pressure vessel, not in the end caps. So I have a tangential or hoop stress, a radial stress, and a longitudinal stress. And these equations 349, are indifferent to the wall thickness. They work perfectly fine for a thin-walled pressure vessel. So you don't have to write two different sets of equations. In this spreadsheet, I have inputs in orange over here, which are my internal pressure, my external pressure, my internal radius, my outside radius, the difference between the internal and external radii, and the increments. Divide the wall thickness into 100 discrete steps. So given the difference between the internal and the external radii, then I end up with a step size of 0.04. Now you will notice if you look at these equations 349 that the length is squared in the numerator and the length is squared in the denominator. So the length units cancel. The units of stress are the same units that we input for the units of pressure, either interior or exterior, acting on the pressure vessel. And so it is indifferent. The equations are indifferent to whether or not we're using English or metric units. You simply get as output the pressures measured using either your English or metric unit system. And so I start with the inner radius and then I add 100 increments to that inner radius of 0.04 in each case until I get to the outermost boundary. I then use the equations that are shown on the right here, to calculate the hoop stress, that's sigma t, the radial stress, that's sigma r, and then if P0 is 0, I easily calculate the longitudinal stress. You can modify this longitudinal to include an outside pressure simply by, in the numerator, subtracting P0 times R0 squared. External pressure not being equal to 0 is no big deal. In fact, in the longitudinal stress, if you look on my spreadsheet, you will see that that's exactly what I do. I multiply the internal pressure, that's B2. I multiply it by the internal radius squared. I subtract from that the external pressure multiplied by the outside radius squared and divide that by the difference between the square of the outside and inside radii. So it's easy to calculate all of these stresses. You'll notice that the longitudinal stress is constant. So in the FEA analysis that I showed just a minute ago, I calculated a hoop stress, and the hoop stress that we got from the FEA was 468 megapascals. Well, if I look at the hoop stress that I calculate using this formula, you will note that the hoop stress varies from the inside inside to the outside, and that the average of that hoop stress is 456 MPa. So we're in the same order as the FEA analysis, and you can use these equations to validate the FEA analysis. So we're within 10%, everything is okay. Let's go back to our spreadsheet for a minute, because you don't write a spreadsheet to solve one problem. You write a spreadsheet so you can solve lots of different problems. And the way this is set up, you can do just that. So let's imagine that instead of a 40 MPa internal pressure, I also add a 10 MPa external pressure. What does it do? It changes the results. So you'll notice that it changes my maximum hoop stress. What happened to my maximum hoop stress? It went down. In fact, I should be able to go down this radial stress. You'll see that I start at 40 internal, and I'd better end at 10. So let's go down the radial stress and see if sure enough I'm at 10, and I am. So that worked out well. What if we change the thickness of our pressure vessel? Let's go ahead and make the internal radius 48 instead of 46. How does it change things? You can see that by making it a thinner wall, the maximum hoop stress has gone up quite a bit because it's thinner. It's got to carry the same pressure, but it's thinner. Let's get rid of the external pressure. Let's take that down to 0. What does that do to it? Makes it even more dramatic. Rises up the maximum hoop pressure even more, but we notice little change in the radial pressure. Of course there's no change in the radial pressure. It's beginning to look like a thin-walled pressure vessel, so you don't see a lot of variation in the stress as you move through the thickness. So instead of, let's go back to a thick-walled pressure vessel. Let's go 40 as an internal radius, and we'll notice a very dramatically different sort of functional form. And I'm going to go ahead and change this. It drops off much more dramatically, both the radial. We solve many different problems by building a single spreadsheet.